All right, so today we're going to look at the behavior of a polynomial, what it does at the ends, how many x-intercepts, how does the degree affect the behavior, things like that. So if we look at the degree of each one of these, the first one here says f of x equals 2x minus 3. Well, the degree is always the power of your biggest exponent. So the only exponent that's really here is x equals 1. As you can see right there, that would be 2x to the first, so the degree is 1. On the second one, we have negative 4x to the first, so that would be degree 1. On the third one, we have degree 2. These are all quadratics, so they're both degree 2. Our cubics are degree 3. And you'll notice all of these are degree 3. Degree 4. We don't have a special name for those, but all of these guys are degree 4. So whatever you see for the largest exponent, that's actually the degree of your polynomial here. Okay? So you just need to know what it means when we talk about degree. And we could go higher. We could go, up as high as we wanted on those polynomials. All right? So some of the things that are going to affect the behavior of a polynomial are the lead coefficient. The lead coefficient is the number in front of your variable. I'll highlight the first few here. So the lead coefficient goes with the largest exponent. So there's my lead coefficient 2. There's my lead coefficient negative 4. There's my lead coefficient positive 4. There's my lead coefficient negative 1. Okay? So we want to look at what happens when the lead coefficient changes as well. So this one would be positive 2, negative 4, positive 4, negative 1, positive 3, negative 1, negative 2, positive 1, because this is 1x to the fourth, positive 4, and positive 2, and negative 1. Okay? So lead coefficients. All right? And then we want to look at the turns in the graph. Are there any turns in the graph? So as we look at the number of turns, all right, we're also going to look at y-intercept and the number of x-intercepts. Okay? So we're going to look at the number of turns. Now, on this first one, I hope you would be able to tell me that y equals 2x minus 3 doesn't turn at all, because this is a straight line. So this is a straight line graph, which means there are no turns. The second one is also a straight line. There are no turns. Now you might be able to tell me some of the others as well, but we'll take a look at those. The other thing that we're going to do, besides looking at turns, is we're going to look at the right and left behavior. When we say what's happening on the right side, what we're basically saying is as x goes to infinity, all right, so as x gets large, that's what this is saying. As x gets big, all right? As x gets big, what's happening to the y values? Okay? So as x goes to infinity, y is going where? And basically that where is y going up or is y going down? If y is going up, we say it's going to positive infinity. If it's going down, we say it's going to negative infinity. Same thing on the left side. We want to know what the behaviors are. So what we're going to do here is, instead of writing out every single time as x goes to infinity, we're going to do it like this. We're going to say, I think what we'll do here, we're going to start on the right side purposefully. So we're going to just let this side of this be as x goes to infinity. And then on the right side over here, we're going to do as x goes to negative infinity. And there's a reason, again, that I'm starting on the right side of this. So let's take a look at this graph. Let's look at the behaviors. What's happening on the right side of this graph. So if you take a look at my line here, this is y equals 2x minus 3. So when we talk about x going to infinity, we talk about x going to the right. As x moves to the right, is this graph going up or is it going down? You can obviously see that as x gets bigger, y is getting bigger. So we would say that as x goes to infinity, y goes to infinity. And Just like that, we also want to look at what's happening as x gets smaller. So as x is heading out towards negative infinity, what's happening to my graph here? So we want to be able to tell both of those things. Now, as x is getting smaller, my graph is going down, so we would say that y goes to negative infinity. All right? So as x goes to positive infinity, y goes up, so we say that y goes to infinity. As x goes to the left, y goes down, so we would say that y goes to negative infinity. The y-intercept and the number of x-intercepts. Let's go back to the graph for a minute. My y-intercept is right here at, what do we got, a scale of 5 here? So -1, 2, 3, so 0, -3. And I have a total of 1 x-intercept on this graph. My y-intercept, 0, -3. X-intercepts, there are 1 of them. I didn't ask for the location of that, I asked for the location of the y-intercept though. Now you'll notice, again, this is a linear function. So hopefully you recognize that this -3 right here, that's my y-intercept. So I should already know that. So based on that, on the next one, I should know that the next one's going to be 0, 5. Let's check it out and let's check the behaviors out and let's see how many x-intercepts we have. So we're going to go back here, take off that guy, put on the next one. Now this graph comes down. Hopefully that makes sense because the graph is y equals -4x. Okay, so that's a negative slope, which means it comes down as you lead from left to right. My y-intercept is 0, 5. I have exactly 1 x-intercept on this graph. It's a straight line. So we would say that as x goes to infinity, so as x gets to the bigger side, y is going down, down, down. As x goes to the smaller side, as x moves to the left, this graph is going up. So we would say that as x goes to infinity, y goes to negative infinity. And as x goes to negative infinity, y goes to positive infinity. So in other words, what we're saying is as x gets big, y gets small. And then as x gets small, y gets big. Okay? So again, this is our heading that we're looking at using for each side of this problem here. Okay? So this is, keep in mind that we're actually looking at 2 different parts right here. Okay? All right. Let me finish up my line here. All right. So let's go back and look at the next one. We said we had 1 x-intercept on that guy as well. So we'll finish that up, 1 x-intercept right here. Okay, let's look at the next one. The next one says how many terms? Again, what's the behavior? As x goes to infinity and negative infinity, where's the y-intercept? And how many x-intercepts? So let's take a look at that next graph. Now, again, some of you may recognize this already, but I'm going to put it up here. This graph has 2 x-intercepts. I can see those. It has a y-intercept right here, and Desmos will actually give me the coordinate 0, -1. So 2 x-intercepts and a y-intercept 0, -1. So 0, -1. Now, and 2 x-intercepts. Now, again, if you know anything about y-intercepts, you know that a y-intercept just means plug in 0 for x. So if I go back here to my function, and if I plug in 0 here, that's 0. If I plug in 0 here for x, that's 0. All I'm left with is -1. So that term that's hanging out there, look at the next one. Plug in 0, this term goes to 0. Plug in 0, this term goes to 0. All I'm left with is this number that's hanging out by itself at the end. That's called our constant term. All right? So this next one would be 0, -9. Let's look at the left and right on that last graph. So as x goes to the right side here, as x moves to the right, the graph is heading up. So as x gets big, y gets big. So we would say as x goes to infinity, y goes to infinity. On the left side, as x gets smaller and smaller and smaller, y gets bigger and bigger and bigger. So as x goes to negative infinity, y goes to positive infinity. So this time, y is going to positive infinity on both sides of the graph. Okay? Y goes to positive infinity on both sides of the graph. All right? Let's look at the next one. All right, so here we go. We'll take off that guy. Okay, so this time our graph is going down, which hopefully, again, that makes sense because we have a negative lead term here. All right, notice that it looks like I only have one x-intercept according to Desmos. So this is a parabola that's facing down. I have a y-intercept at 0, -9. We already saw that on the other sheet. And we only have one x-intercept. So we have one x-intercept on this guy. Both sides are going down, so as x goes to positive infinity, y is going down to negative infinity. And because it's a parabola, both sides do the same thing. Y goes to negative infinity as x goes to negative infinity. All right? The number of turns, we didn't talk about that, I missed that. So if you look at those graphs, both of them, they both turn one time exactly. It comes up from the left on the orange graph, and then it turns and goes down. The green graph comes down on the left, turns and goes up. So each of those graphs have one turn. Okay? One turn here and one turn here. Now at this point, I would encourage you to turn off the video and actually try some of these on your own and see what you can come up with for the rest of the graphs. As you're doing that, look for patterns across the rows, down the columns, wherever you can think of to look for a pattern, try and find a pattern. Okay, so now that we're back, this next cubic, and I'm going to show the next couple, but then I'm going to stop and just fill in the rest because hopefully you did turn off the computer. So this next cubic, if we go look at that guy, all right? So notice my y-intercept right here at 0, 1. Look at that last term in that equation. It says +1. This guy also has 1, 2, 3 x-intercepts, and it turns 1, 2 times, all right? Now let's talk about x going to positive infinity. On the right side of this graph, as x moves to the right and gets bigger, the graph goes up. On the left side, as x moves to the left, the graph goes down. So we would say that x is going to negative infinity on the left side. So our behaviors. Number one, this graph had 2 turns. As x goes to infinity, y also went to infinity on this graph. As x went to negative infinity, y went to negative infinity. The y-intercept was at 0, 1, and it actually had 3 x-intercepts. Next graph. All right. Look at this one. A y-intercept at 0, 3, only a single x-intercept at, wow, 0.769, so only one x-intercept. But I hope you can see that, let's say that we were to take this graph and shift this graph down a little bit. Okay? So if I were to shift this graph down just a little bit, I could actually make this point that's down here, I can make that sit right on the x-axis. Okay, I can make that point come and sit right down in this area right here. Okay? And if I dropped it a little bit more, I could actually have that point below the x-axis, and I would be touching the graph 2 more times, like maybe here and over on this side here. Okay? So this graph has one x-intercept, but with a slight tweak to the equation, we could actually bring it down and make it have as many as 3. Okay? So we have 2 turns still. The right side of this graph, as x went to infinity, you saw that the right side went down and the left side went up. So y on the right side goes down, that's negative infinity. Y on the left side goes up, so y goes to positive infinity. Y-intercept at 0, 3. And in this case, we only had 1, but we talked about the fact that if we were to shift the graph just a little bit down, we could actually see 2 or 3. Okay? One more, and then I'll fill them in here. 4th degree, last one that I'm going to show here. So look at this 4th degree. I've got 1, 2, 3, 4 x-intercepts. All right, another guy over here. I've got a single y-intercept at 0, 2, which again makes sense if you look at that last number in the equation. It says +2. And I've got, wow, I mean, there's another turn on this guy somewhere up in there. You can see that if you just go down up on the graph there. So I've actually got a total of 3 turns on this graph as well. And both sides go down. So kind of like a parabola behaves, this guy's behaving the same way a parabola does. All right, so we had 3 turns. Let me change colors here again. We had a total of 3 turns. The right side went down, so as x went to infinity, y was going to negative infinity. As x went to negative infinity, on the left, y also went down to negative infinity. We had a y-intercept at 0, 2, and we actually had 4 x-intercepts. All right? So the next one, this is a degree 4 with a lead coefficient of 1. All right? This guy here has 3 turns as well. The right side of this guy, if you graphed it on Desmos, you would have seen that the right side went up. So as x goes to infinity, y goes to infinity. The left side did the exact same thing. The y-intercept is 0, 4. Again, that's that constant term at the end right here, 0, 4. And it had 4 x-intercepts. The next one down here had 3 turns as well. The right side went up, so y went to positive infinity. The left side also went up, so y went to positive infinity. A y-intercept at 0, -2. And this graph only had 2 x-intercepts. Let's take a look at that one. So only 2 x-intercepts. Look at that. So you'll notice I've got my x-intercepts, but again, I just want to show you guys that if we were to shift this graph, you see this little maximum point right there? If we were to shift that graph up a little bit, we could actually make that maximum hit the x-axis, and then we'd have 3 x-intercepts. Or if we take that point off for a minute, look at these 2 points right here. Those 2 points, if I were to move it up just a little bit further, so that those 2 points were just below the x-axis, I would actually hit 2 more times somewhere in this area as well. So I only have 2 x-intercepts, but I could have as many as 4. And if we push this graph way, way up, see this point down here at the bottom? If I were to push that up over my x-axis, this thing wouldn't touch the x-axis at all. Okay? So this is a 4th degree function, and if I were to tweak it just a little bit, I could see that I could reduce the number of x-intercepts, I could increase the number of x-intercepts, so I could have anywhere from 0 to 4 x-intercepts on this guy. All right? Next one. 5th degree. This guy had 4 turns. The right side, as x got really big, y went up. The left side, as x went to negative infinity, the left side of this graph went down, so y went to negative infinity. We have an a y-intercept at 0, -3, and this graph had a total of 5 x-intercepts. That's a lot. Next one had 4 turns. You'll notice that the right side went down again. So as x got really big, y got really small and went to negative infinity. The left side of this graph went the opposite direction. The left side was going up to positive infinity. We had a y-intercept at 0, 0, because again, notice if you plug in 0 to this function, you get 0 for the first term, 0 for the second, 0 for the third, 0 for the fourth, and 0 for the fifth. There's no constant term here. And this graph did have a total of 5 x-intercepts. Now again, at this point, I would encourage you to try and look for some of the things that you notice. What do I notice about the degree versus the number of terms versus the number of x-intercepts? What do I notice about the right and left behaviors? What's special that gives me something to do with those? All right? All right. So a polynomial, there's some things that we want to know about polynomials in order to sketch these things. Number 1, they are continuous. All right? They're continuous. You'll notice none of those graphs had any stops and starts or anything like that, and they have smooth terms. every one of those graphs had nice smooth curves, no sharp edges or anything like that. All right. If they had a degree of, let's say, n, okay, so let's just say n equals 5, okay? If n were to equal 5, then our graphs showed 4 turns, a maximum of 4 turns, okay? It's if n was equal to 2, so this would be an instance of a quadratic. A quadratic always has that 1 turn just like that. So if n was equal to 2, if it was a degree 2, I would only see 1 turn. All right? So with degree n, it can only have n minus 1 turns. It's always going to have 1 less turn. I shouldn't say always. It can have at most 1 less turn than the degree. What do I mean by that? It means that there are actually 4th degree. Okay? I could have a 4th degree polynomial. Looks like this. It only has 1 turn, but I could also have a 4th degree with 3 turns as well. Okay. With degree n, so if I had a degree 4, I could have 4 x-intercepts. If it was degree 2, I could have 2 x-intercepts. But you'll notice the word here, at most. So with degree n, the maximum number of x-intercepts is the same as the degree. It can always have less. All right, we saw some examples of that when I was talking about sliding graphs up and down. I'm going to go back to my 3rd degree here for a minute. So if this was a 3rd degree, it could hit the x-axis 3 times. 1, 2, 3. But if I were to shift that graph up just a teeny tiny bit, I could make it hit the x-axis up, down, curve around, boom, just like that. I could make it actually hit twice. Or if I shifted it up even further than that, right, I could actually make it look like this, where it only hits once. But I don't care how far you shift it up, that polynomial will always hit the x-axis at least once, because one side goes up and one side goes down. So if one side goes up and one side goes down, you're always going to touch at least 1 time. All right? So if it has degree 7, you can have at most 7 x-intercepts, but you got to have at least 1. If it's a degree 4, you could have 4 x-intercepts, but even this 4th degree that I drew over here earlier with 1 x-intercept, if I were to bump that up, it could have no x-intercepts. And the reason it can have none is because both sides are going the same direction. All right? These guys rise to the right. So that's why we talked about right-hand behavior first. They rise to the right if the lead coefficient is positive. So go back and look at some of those graphs. If the, if I had a 2x squared parabola, the right side's going up and the left side's going up. So we would say as x goes to infinity, y also goes to infinity. They fall to the right. Oops, they fall to the right if the lead coefficient is negative. In other words, if it started off with a negative, then the right side always went down every single time. So as x goes to infinity, y would go to negative infinity if I had a lead coefficient that was negative. Polynomials with odd exponents. So we're talking exponents of 1, 3, 5, 7 have the same behavior as linear equations. All right, so when we talk about the same behavior, we're talking about the same right and left behavior as linear equations. A linear equation either goes up one side and down the other, or if it has a negative slope, it goes down one side and up the other. Every odd function will also do the same thing, like my function that I drew over here on the left side. This function is a 3rd degree function. 3rd degree. Okay, that's my intention. Notice the right side goes up, the left side goes down. But I just as easily could have drawn a 3rd degree function that looked like this, where the left side was up and the right side is down. So odd exponents will always go opposite directions on the right-left behavior, and even exponents will always have the same right and left behavior as quadratic equations. In other words, a quadratic, both sides either go up or both sides go down. So a fourth degree will always do both sides up or both sides down. And they have y-intercepts at 0, comma, wherever my constant, whatever my constant term is. Remember, the constant is that term that hangs out at the end of the polynomial. Okay, so my constant in this polynomial is a sub 0. All right, that constant never has an x next to it. So this would be 0, comma, a sub 0, where that's just some number. Okay, let's keep moving on. All right, so now what we want to be able to do is we want to be able to use all that information to graph these polynomials. And so the first thing I want to do is, you'll notice my polynomial is already in factored form, and we've been talking about factors versus x-intercepts of a polynomial. And so one of the first things I'm going to do is I'm going to start to look at all this information that we just talked about. What's the degree of this thing? Now, to find the degree, because it's already in factored form, you'd have to kind of ask yourself, well, if I were to multiply all these factors together, what degree would that be? So just think about it as x times x is x squared times x would be x cubed, and x cubed times x would be x to the fourth. So this is some x to the fourth, so that means it's a degree 4 function. Okay, well, if it's degree 4, it can only turn up to 3 times. The right-hand behavior, as x goes to positive infinity, I have a positive lead coefficient here. So that means that y would also go to positive infinity. And the left behavior is determined by the degree. Since this is an even degree, both sides have to go the same direction. So y on the right and the left are both going to go up. The y-intercept on this one, not quite as easy to find, because I have to actually plug in 0 for x to find it. All right, so let's do that. Let's find our y-intercept. So I'm going to do some scribbling up here. So f of 0 equals 0 times 0 minus 2, 0 plus 3, 0 minus 4. So if you look at these, 0 minus 4 is negative 4, that's positive 3, that's negative 2, and that's 0. So really what I'm doing is I'm multiplying negative 4 times 3, which would be negative 12, negative 12 times negative 2, which would be positive 24, and positive 24 times 0, which is 0. So f of 0 equals 0. Check it out. There's my y-intercept and my x. I'm going to graph that guy right away since we're going to sketch this. How many x-intercepts are there? Now, in order to find your x-intercepts, you have to take your factors and set them equal to 0. So let's do that. We're going to do x, that's my first factor, equal to 0. My second factor, x minus 2, equal to 0. We solve that, we get x equals 2. My third one, x plus 3, equal to 0. Solve that, you get x equals negative 3. My last one, x minus 4, equal to 0. You solve it, you get x equals 4. So this problem has a total of 4 x-intercepts. They are all real. And I can even graph those now. So let's do that. I've got my 0, I've got one at 2, I've got one at negative 3, 1, 2, negative 3, and one at positive 4 over here. Now, here's the cool thing about doing these. We already have some information about this graph. We already know that the right and the left sides are both going to go up. Now, this is the last x-intercept that I found. So my graph has to go up from there. Here's the deal. It can't do this, because otherwise I just created another x-intercept here and here, and I can't do that. So what I have to do is use the intercepts to help guide me in drawing this. And the drawing doesn't have to be perfect, but you should have the right amount of behaviors right. You should have the intercepts right. We're going to label some maxes and mins here. And so the left side of this guy is also going to go up. Oops. Okay, so my left side's going to go up from there. Now, what's it doing in between? Is it going to bounce off of this x-intercept and go back up in the middle here like this? You know, is it going to go down through there and around like this? We don't really know what this thing's going to do. Well, maybe we do, maybe we don't. But one of the things I can do is I can simply create a small t-table and just pick some values in between my intercepts. All right? So if I was going to do that, I might pick, let's see, what are some good values of x to pick here? So I might pick one between 0 and -3 just to see what's going on. So maybe I pick -1. And then I'd definitely pick +1 because that's in between 0 and 2, and then +3. Now, if you plug those into the function and you do your math, -1 gives you -30, +1 gives you 12, and 3 gives you -18. Now, I obviously can't fit some of those without changing my scale. So the biggest number I need to fit is -30. So I'm going to have to change my scale, and I'm going to have to rescale. And in order to do this, I'm going to have to change my y-axis to go, and I think I can do this by 5s. So I'm going to leave my x-axis at 1s, but I'm going to change my y-axis to 5. So when I go to plot -1, -30, I'm going to go -1, and then -5, 10, 15, 20, 25. There's -30. 1, 12, that would be 5, 10. So 12 is going to end up in here. I don't care. It's perfect. 3, -18, 5, 10, 15, 18 is going to be somewhere in this area. So now I can kind of see what's happening. My graph is coming down this direction. It's going to hit this point. It's going to come back up through the x-intercept, bump into that point, back down, bump into this point, and back up just like that. Now, could this graph go down further on the left side? Absolutely. We don't know exactly how far down it goes. Just like the little curve on the right side here. Both of these guys are called, well, actually I need to stop there for a second. The way this graph is drawn, this dude over here, this is a minimum, but we call this guy a local min. We call him a local min because he's not the shortest, he's not the lowest rather. This guy is the absolute lowest. This guy's like, hey look, I'm the absolute min. Nobody's lower than me. Absolute min, or minimum. All right? Now you'll notice on the right and the left, the graph goes up forever. So there's no absolute max, but there's a local max right here. So we would call that point a local max. All right? And then a domain and range for this guy, because this graph moves forever to the right and to the left, the domain would have to be x in the set of reals. The range would actually be very difficult to figure out on this, but according to my picture, the range would go from -18 at the lowest y value up to infinity. Now, keep in mind, hang on, I gotta see what happened here. So what you gotta keep in mind here is that this y value here in this interval from -18 up to infinity, this is just an estimate. All right? It definitely goes to infinity at the top end, but the -18 is just an estimate based on what you see on your picture. All right? So let's take a look at the next one. All right? What's the degree of this function? Now this time, this one's a little weird because last time all I did was multiply the x's together, but you're going to notice right here, I've got 2 x plus 4's right here. So really what I'm looking at here is an x plus 4 and a second x plus 4. All right, so what difference does that make? It makes a difference when I go to multiply my x's. I've got -x, or I've got x times x times x times x. That's x to the 4th. That's a degree 4 function again. Well, we know that this could turn up to 3 times. We see the negative out in front of that first factor there, so as x goes to infinity, we would say that y goes to -infinity. So we're going to be going down on the right. Because it's degree 4, the left side's going to go the same direction, -infinity. The y-intercept, again, if we plug in 0 and you do the math on this guy, you're going to end up with a y-intercept of 80. All right? So just, I would suggest, you know, because we're probably going to end up doing a small t-table here anyway, I would just automatically throw 0 into my t-table. All right, and that gets me my y-intercept, 0, 80. How many x-intercepts? Well, let's take our factors again. We have x plus 1 equal to 0, so that's going to give me one of them at x equals -1. I have x plus 4. I actually have 2 of those. Now, I'm not going to list them twice, but I'm going to list x equals -4, but because there's 2 factors, I'm going to call this a double solution. A double solution here. So this solution here is called a double solution or a multiplicity of 2, okay? So we'll call it a double for now, but we'll use the word multiplicity as well. And so that counts as 2 solutions right there, all right? So on a degree 4 function, we should have 4 solutions. We have x equals -1, we have 2 x equals -4s, and then we have our last factor, x minus 5 equal to 0, and if you solve that, you get x equals +5. So I actually have a total of 4 solutions, although one of them is a multiplicity of 2. Let's graph these and see what we got here. All right, so we have -1, we have -4, we have +5, and then we have a y-intercept at 0, 80, okay? Now, before I graph that, I'm actually going to do a t-table because I don't know how much higher I'm going to need to go. So I might choose a point. Well, I'm going to get 0 out of there in a minute. So I've already got 0, 80. I'm going to do another one at -2. So if I did -2, that gives me a value between these 2 intercepts over here on the left. And at -2, the value would be -28. All right. Now, if you wanted to do some more over in here, you could. I've got them all listed. So if I wanted to do 3, for instance, +3, even though I already have 0, I could do 3. And that actually puts me way up there at 392. So that thing's like way, way up there. Okay. So I may or may not want to graph that, but I'm just going to, again, change my y-axis. Because in order to graph these, I've got to have something that I can actually graph. And so I'm going to go by 50s on the y-axis. All right. So here we go. My y-intercept is 0, 80. So there's 50, 100. So that would be just a little bit below 100. At -2, you're at -28. So that would be -50. So -28 is going to be in this area. And then at +3, we're at 392. So we'd have to count up 51, 52, 53, 50, just under 400. And let's take a look. The right and left sides are both going down on this graph. So I'll graph down here and down here. And somehow in here, we've got to connect all of these guys. Okay, so we've got these guys that are connecting in through here, like that. And that would make sense, because if I kept going up and around through that upper point and back down through my intercept at 5, that makes sense with the curvature of the graph. But on the other side here, you'll notice that if I try and graph this, I can't come up and around like this because I just ended up creating another intercept, and I don't have an intercept right there, so that can't be possible. The only thing that could be happening here is if this graph came up and under and just sort of bounced off and went back down like that. And that's what a double solution does. A double solution will actually give you a bounce off of the x-axis. Bounce off x-axis. All right, and that's true of a double, of a multiplicity. So that's a multiplicity of 2, or a multiplicity of 4, a multiplicity of 6. They will all do some sort of bouncing like you see right there. The domain on this guy is x in the set of reals. The range is, according to my highest value here, remember my point value up here was 3,392. Now this graph could be going higher at 4 or 2. We don't know that, so our range is just an estimate. And so we would say that the range is -infinity, 392, just simply keeping in mind that 392 is an estimate. All right? And technically, since I do hit 392, the right side of this should be a bracket and not a parenthesis, and should have been a bracket on the previous problem as well. Okay? Okay, so let's go down to the next one here. Let's see what we can do with this one. We have two factors on this one, but each factor has a different exponent on it. So this x plus 1 to the third power really means 3 factors of x plus 1. And the x plus 6 is a degree 2, so that's 2 factors of x plus 6 for a total of 5 factors, or a degree of 5. The maximum number of terms on that can be 4. The right-hand side behavior, as x goes to infinity, y is also going to go to infinity because it doesn't lead with a negative. And because it's degree 5, the left side will go the opposite direction of the right side. So on the left side, as x goes to negative infinity, y also goes to negative infinity. My y-intercept on this, again, if you plug in 0, I would put that in your t-table right away and just count that as one of those points that you want to find. The y-intercept turns out to be at 0,36. All right. How many x-intercepts? Well, there's only 2 distinct factors, so there can only be 2 x-intercepts. X plus 1 equal to 0 gives me x equals negative 1, and x plus 6 equal to 0 gives me x equals negative 6. So I have 2 x-intercepts, but it counts as a total of 5 solutions. So the x equals negative 1 that had a degree 3 on it, we call this a multiplicity of 3. And this guy here, x equals negative 6, this is a multiplicity of 2. So it counts for a total of 5 solutions. So I have an x-intercept at negative 1, an x-intercept at negative 2, 3, 4, 5, 6, a y-intercept at 0,36, and I might want a couple other points on here just to see what's going on here. So I'm going to do, I'm going to choose something in between here. So I'm going to choose like maybe negative 3 or 4. So I'll go with negative 4. And negative 4 goes down to negative 108. And if I choose, actually that should do it because I have to go up on the right and down on the left. So right away I could have done this up on the right. Oops, I guess my y-intercept would help there too. So I'm going to need to go scale down to negative 108, and so I'm going to go by tens. So I'm going to change my y-axis to go by tens. So I can graph my y-intercept at 10, 20, 30. 6 would be somewhere right around here. The right side of my graph is going up like that. At negative 4, negative 1, 2, 3, 4, I need to go down negative 108. So that's 10, 20, 30, 40, 50, 60, 70, 80, 90, 110, so negative 108 would be down in there somewhere. All right? And on the left side of this graph, I also have to be going down this direction. Now, take a look at my multiplicities here. We talked about this on the last problem. If I have a multiplicity of 2, this is a bounce. All right, so my graph should be bouncing off the x-axis at negative 6. And that makes sense because if I bounce right here at negative 6 and I come back down, I will eventually hit this point at negative 4, negative 108, and I will come back up and hit that point. Now, notice that multiplicity there is 3. Multiplicities, odd multiplicities go through. Odds go through. And that shows with what's going on because that red part of the graph would come up through that point at negative 1 and continue on to positive infinity. The domain on this graph, x in the set of reals. The range on this graph is y in the set of reals because the right side goes up and the left side goes down, so it goes on forever in both directions. At this point, I would encourage you to turn off the video and try the last one on your own and see what you can do with it. All right, so the degree of this function is a degree 10 because I have 3 x's with x minus 3, 4 x's with x plus 2, and 3 x's with a negative x out front. So degree 10, up to 9 terms. The right side, as x goes to positive infinity, y goes to negative infinity. Oops, forgot the negative there. Left side, because it's degree 10, the two sides are going to go the same direction, so y is going to go to negative infinity. The y-intercept, if I plug in 0 here, I am going to get out 0 here as well. So not only is 0, 0 my y-intercept, 0, 0 is also going to be one of my x-intercepts. We'll see that in a minute. Take each factor and set it equal to 0. So x cubed equal to 0. If you cube root both sides of that, x has to be equal to 0. So there's that x and y intercept match right there. X plus 2. This is, oh, by the way, this is a multiplicity of 3. Multiplicity of 3. X plus 2 equal to 0. You solve that, you get x equals negative 2. Since it was degree 4 on that factor, this is a multiple of 4, which means it's a bounce. So this is a bounce. The first one's going to go through because it's odd multiplicity, and the last one, x minus 3 to the third power. So that's going to be x equals 3, multiplicity of 3. So that's going to go through the x-axis as well. So we have 0, we have negative 2, and we have positive 3. If you were going to do a t-table here, I would probably just choose a couple of values, maybe one at negative 1 and one at positive 1, something like that. All right. So at negative 1, this graph's going to be down at negative 64. At positive 1, it's up at 648. It's crazy. So we're going to need to change our scale big time on this, but I'm just going to estimate it this time. All right. So at positive 1, I'm just going to call this right here 648. I don't even care at this point. Notice my right behavior goes down. It's a degree 10, so the left behavior goes down. There is a bounce at negative 2, so we have to go through, and my negative 1 value is, let's see here, we had a bounce at negative 2, so the bounce should be happening here, and at negative 1, that would make sense because at negative 1 I was at negative 64, so a bounce off of here would come back down, around. I'm going to go through the graph at 0 because it was a multiplicity of 3, which makes sense again because I would lead up to my max there and back down and through the graph again at x equals 3. So I didn't label these last time. This guy here would be an absolute max because it is the top of my graph. Now, chances are my graph does go a little bit higher at x equals 2. I'm not going to worry about it. This guy here is a relative min because he's not the lowest min, he's just a relative min. This guy over here is a relative max because he's a max, he's just not the highest max. And there is no absolute min on this graph because it keeps going down forever. Domain, x in the set of reals again. All polynomials are x in the set of reals. Range, if we were going to estimate, okay, I would be estimating off that 648, so I'm not even going to mess with the range on this guy here. All right? So a couple of quick things and we'll wrap this up. If g of x were to equal positive x cubed, right? Notice my last one, same equation as the last one, but what if it were to equal positive x cubed? How would it compare? A negative in the front. All it does is it would reflect the graph. So the graph would reflect over the x-axis, just like we talked about in Unit 1, over x-axis. All right? And then the last two questions here, what happens on the graph when you have factors with even degrees? So if this was x minus a to the second or the fourth or something like that, we know that the graph will bounce. The graph will bounce off the x-axis. And with odd degrees, 1s, 3s, 5s, the graph will go through the x-axis. It will go through the x-axis. All right? That was a long one, but hopefully it made sense.